Hi everyone. In this video, we're going to discuss trigonometric and other substitutions that we can use to help us evaluate indefinite integrals. In particular, in this video, we're going to review some important trig functions and identities related to those trig functions. We'll learn how to use trig substitutions to simplify integrals. And we'll also understand trigonometric substitutions as just one type of a larger system of integral substitutions, which can be used to help simplify integrals. So to begin, let's do a quick review of the unit circle. So you may remember in a pre-calculus or trigonometry class, right, first learning about the unit circle. Right, the unit circle is the circle of radius 1 centered at the origin. Okay. And it relates to the trig functions because we define the values of the trig function. So imagine that you measure some angle theta from the positive x-axis. Okay, then the point at which this line segment intersects the unit circle is the point cosine of theta sine of theta. Okay, so in particular, viewed another way, this distance is simply cosine of theta, while this distance is sine of theta. Okay, and you can already sort of see, because of the way I've drawn this, that this clearly also relates to right triangle trigonometry. Okay. So when we think about a right triangle, one way we may also want to think about sine of theta and cosine of theta. If I think about the side opposite an angle, the side adjacent to that angle, and the hypotenuse of this right triangle, okay, then sine of theta is the ratio of the length of the opposite side to the length of the hypotenuse. Cosine of theta is the ratio of the adjacent side length to the hypotenuse length. And tangent of theta is the ratio of the opposite side length to the adjacent side length. So just to sort of remind ourselves where all of these trig functions come from, they come from either thinking about sort of this unit circle notion or this right triangle notion. And both of these will be helpful as we go through the rest of this course. If you need additional review on these topics, come see me and I'm happy to provide resources. But this is assumed prerequisite knowledge. We will do a little bit more review of some specifics, but I'm not going to spend too much time reviewing these items. Now, additionally, we can remind ourselves of some other trigonometric identities. In particular, we have these additional trig functions. So the first that you see here is cosecant, then secant. We've already discussed tangent, but tangent is the ratio of sine to cosine, and cotangent, which is then 1 over tangent of theta. So in particular, cosecant, secant, and cotangent are defined as the reciprocals of sine, cosine, and tangent, respectively. This will, again, be important, particularly if we think about in terms of a right triangle, right? Sine was the ratio of the opposite side length to the hypotenuse. And so cosecant of an angle would be the hypotenuse over the opposite side. And you could continue with these for secant and cotangent as well. Now, there are some additional trigonometric identities, often called the Pythagorean identities, which relate the trig functions as well. And in particular, these go back to that notion of the unit circle. Okay, so if I think about drawing my unit circle here, right, and so we said, okay, this is a point on my unit circle with angle theta measured between that line segment and the positive x-axis. Then this distance, if I drop a perpendicular, is cosine of theta. this distance is sine of theta. And by the Pythagorean theorem, the sum of the squares of the legs of the right triangle should be equal to the square of the hypotenuse. So in this case, we should have that sine of theta squared plus cosine theta squared is equal to 1 squared, which of course, when simplified, gives us this first identity. Okay, so this first identity simply comes from the fact that sine of theta and cosine of theta are defined as these quantities related to the unit circle. The rest of the identities can in fact just be derived from some manipulations of the first identity. Okay, so if I take that first identity, sine squared plus cosine squared equals 1, and I divide everything through by sine squared of theta. So if I were to take sine squared theta plus cosine squared theta is equal to 1, and I divide everything by sine squared of theta, well, sine squared of theta divided by sine squared of theta simplifies to 1. This is the same as cosine of theta over sine of theta squared, and cosine over sine is cotangent. And then 1 over sine squared is cosecant squared theta. So actually, mistakenly, by deriving through by sine, I actually derived this one, okay? To divide by sine of theta, sorry, sine squared of theta to get there. To get to this other one, you actually divide by cosine squared of theta. So if up here instead, I had divided by cosine squared, then I would get sine of theta over cosine theta quantity squared, which would be tangent squared theta, plus 1 is equal to 1 over cosine squared, which would be secant squared theta. So again, I get this sort of second set of identities here by dividing through by cosine squared theta. Okay, so again, each of these two identities is really just some alternate version of the first, but we're actually going to make use of, well, at least certainly heavily the first two, occasionally the last one as we proceed throughout the rest of this course. Okay. All right, finally, I want to remind you of a sort of type of problem you may have seen in a pre-calculus course, but without context, it may not have made much sense. But we'll see today actually how it can be very helpful for doing trigonometric substitutions into integrals. So if you know the value of one trigonometric function for a given angle theta, then you can find all the values of the other trigonometric functions for that same angle theta using what's called a reference triangle. So for example, let's imagine that I knew that sine of theta was equal to 2/5. If I think of this in terms of a right triangle, and this is what I'm going to call my reference triangle, then sine of theta, which is in this case given to be 2/5, that's the ratio of the opposite side to the hypotenuse. So I might as well create this reference triangle. I want to create it so that sine of theta is 2/5. So I might as well make my opposite side 2 and my hypotenuse 5. Now, if I do that, I can then use the Pythagorean theorem to solve for this missing leg of the triangle. So in particular, this would be the square root of 5 squared minus 2 squared, or 25 minus 4, which is the square root of 21. Okay, so now I have this reference triangle, and I know its legs are square root of 21, 2, and 5. Okay, and now that I know that, I can figure out what secant of theta is. So secant of theta is 1 over cosine of theta. Okay. And 1 over cosine of theta is 1 over adjacent over hypotenuse. So it's hypotenuse over adjacent. And so the hypotenuse here I know is 5. The adjacent side here I now know is square root of 21. And so I'm able to figure out the value of secant of theta based on the fact that I know the value of sine of theta by creating this reference triangle. Now, what if I were to change the problem ever so slightly? And what if instead of having a fixed value, I actually had a variable value for, say, cosine of theta? Okay. Well, again, I can do exactly the same thing. Now my answers are just going to involve the variable x. I'm again going to create a reference triangle. Okay. This time, I'm given that cosine of theta is x over 2. Okay. So I'm given that cosine of theta is x over 2. And cosine of theta, I know, is the ratio of my adjacent side to my hypotenuse. So I might as well create my reference triangle so that the adjacent side is x and the hypotenuse is 2. If I do that, I can solve for the remaining leg here using the Pythagorean theorem. So x squared plus this side squared should be equal to 2 squared. And so this side will be the square root of 2 squared, which is 4, minus x squared. Now I want to calculate tangent of theta. And I can recall here that tangent is the ratio of the opposite and adjacent sides. The opposite side to the angle theta is the square root of 4 minus x squared. And the adjacent side to the angle theta is x. And so again, I'm able to figure out the value of tangent theta based on my knowledge of the value of cosine of theta. Okay. Again, this is going to be helpful in simplifying some problems later. But before we move on, let's do a quick knowledge check. So see if you can find the value of sine of theta, given that secant of theta is equal to the square root of x squared plus 9 divided by x. Okay, great. Let's create our reference triangle first. So we know that secant of theta is equal to the square root of x squared plus 9 over x. Okay. Now, we want to know what secant of theta is in terms of the sides of our right triangle. So I recall that secant is 1 over cosine of theta. That's 1 over adjacent over hypotenuse, or hypotenuse over adjacent. So when I'm creating my reference triangle, I might as well make my hypotenuse be the square root of x squared plus 9, and my adjacent side be x. Now I need to find my opposite side sitting over here. To do that, I'm going to use again the Pythagorean theorem. So let me call this side B. I know by the Pythagorean theorem that my leg x squared plus the other leg b squared ought to be equal to the hypotenuse, which is x squared plus 9 squared. And so I get x squared plus b squared is equal to x squared plus 9. I can subtract an x squared from both sides. And I'll see quickly that b ought to be 3, right? If I'm solving this purely algebraically, b should be plus or minus 3, but it's a length, so it should be positive 3. All right, now I've created my reference triangle, and now my goal is to find sine of theta. Well, sine of theta is the ratio of the opposite side to the hypotenuse. So it is simply 3 over the square root of x squared plus 9. We'll see in just a few moments how this becomes very helpful for simplifying integrals. All right, so to integration, suppose I asked you to find the integral of 1 over the square root of 1 minus x squared dx. Now, there's a possibility that you may remember from Calculus 1 that this is the derivative of a particular inverse trig function. If you remember that, great. But I want to use this as an example. Let's pretend that we don't remember it. And so if we don't remember it, how might we solve this problem? So my idea, and really the main idea for trigonometric substitutions and substitutions in general, is what if I could substitute something in for x so that this integrand became nicer? And in particular, when I'm looking here, I have the square root of something. So what if I could make some substitution? So I'm going to set x equal to some function of a variable theta, so that when I plugged in that thing for x, I got a perfect square under that square root. Having a perfect square under a square root is great for simplifying. That might actually make the integrand easier to work with. So as I look at this, I might wonder, well, what sort of substitution would make sense here? I'd like something so that 1 minus that thing squared becomes something else squared. And if I think back to the trig identities we were looking at earlier, I remember that sine squared theta plus cosine squared theta is equal to 1. And if I rewrite that, that's 1 minus sine squared theta is equal to cosine squared theta. So I might think, well, what if I put in sine of theta here, then I would get cosine of theta there. So let's actually try that substitution. So I'm going to set x to be sine of theta. Now, when I do this, I'm going to be changing my variable because I'm going to be replacing my x's with this function that involves theta. So I can no longer integrate with respect to x. I have to integrate now with respect to theta. So I could take a derivative of this with respect to theta. If I do, right, the derivative is just cosine of theta. And it's often the case, because we want to use differential notation, that we'll just write this as dx is equal to cosine of theta d theta. So it's, again, even though it doesn't technically make sense to multiply by d theta on both sides, it actually works to treat it that way, and so we will. We'll just write dx is equal to cosine of theta d theta. And so now we can substitute all of this into our integral, which becomes the integral of 1 over square root of 1 minus sine theta squared. But now we also need to substitute for dx, which we now know is cosine of theta d theta. So times cosine of theta d theta. Now, if I simplify this a bit, I get 1 over the square root, this 1 minus sine squared theta. We chose that substitution specifically so that this would simplify to cosine squared theta. And now square root of cosine squared would just be cosine. So this is 1 over cosine of theta times cosine of theta d theta. Sorry, that theta is not showing up so well there at the end. And now 1 over cosine of theta times cosine of theta, that's just the integral of 1 d theta. And well, the integral of 1 d theta is just theta plus c. But now, just like with u substitutions, I made up the theta piece. My original problem was something to do with x's. So I now need to convert back. Okay. In this case, I need to solve this for theta. Okay, so if I look at this, I say, oh, okay, in this case, I could just take the inverse sine of both sides. And I would get that theta is equal to sine inverse of x. So this is really sine inverse of x plus c. Now, again, I mentioned at the beginning, you may have just known that the derivative of sine inverse or arc sine was 1 over the square root of 1 minus x squared, in which case you could just do this from knowing that fact. But if you didn't know that, you can actually derive it by doing this sort of trigonometric substitution into the integral. Let's look at other examples to see how this can be used, but also to see ways in which the problems can sometimes be a little more difficult, but we still have the tools to solve them. So let's again look at an integral involving a square root, but now this time I have the square root of 25 minus x squared. Now again, my goal with these problems is going to remain the same. I want to make some substitution in for x that's going to make this thing under the square root a perfect square, right? So before we substituted in sine, that gave us we had 1 minus sine squared, which was cosine squared, under the square root. That was very easy to simplify. We want to do something similar here, but I can't just plug in sine here, right? In particular, if I tried just plugging in sine, right, I'd end up with 25 minus sine squared theta, which, well, isn't equal to anything. So I should say it's not equal to anything useful. So what I need to do here is I want to sort of remember that my goal before was to end up with like a 1 minus sine squared theta. That's what I'd like to end up with, because I know that's cosine squared theta. The problem is I don't have a 1 sitting here, I have a 25. So what if I multiplied this entire expression through by 25? Okay. So I'm just multiplying through by 25. And now if I rewrite this, here I see I could rewrite this as 5 times sine of theta quantity squared. And then I would be left with 5 times cosine theta quantity squared. So here I'm seeing that instead of just substituting in sine, if I were to substitute in 5 sine of theta, then I would end up with something under the radical that is in fact equal to a perfect square. So let's try that substitution and see what happens. So I'm going to now try the substitution setting x equal to 5 sine of theta. Okay. If I'm going to do that, my dx is also going to change because I'm changing the variable of integration. The derivative of this is 5 cosine of theta d theta. All right. So now making the substitution into this integral, I'll get that this is equal to the integral of the square root of 25 minus 5 sine of theta squared. But now my dx is going to become 5 cosine theta d theta, so times 5 cosine theta d theta. All right, now let me simplify the integrand a bit here. One of the themes we're going to be seeing as we move along through some of these methods of integration is that there's some tool, some technique, some trick that helps simplify the integrand, but then a lot of the work just becomes doing some algebra. So in this case, we need to do now some algebraic simplification of the integrand. So if I look at this, this is really 25 minus, if I square each piece, this is 25 sine squared theta times, again, this 5 cosine theta d theta. I can factor a 25 out of each of these terms, and in fact, I can just then pull that out of the square root, and it'll become a 5. So I'll get a 5 times the square root of 1 minus sine squared theta times 5 cosine theta d theta. I can combine these two 5s, 5 times 5 is 25, and pull them outside of the integral. I get 25 times the integral of this piece now is just cosine squared theta, but the square root of cosine squared theta is just cosine theta. So I get 25 cosine squared theta d theta. So now what I have done is I have fully transformed this integral into an integral in terms solely of the new variable theta, right? And I've fully simplified it here, okay? Now the question that I need to deal with, right, is what is the integral of cosine squared theta d theta? Now, if you wanted to do this from first principles, right, what you would do is you would go off to the side and you would say, okay, I need the integral of cosine squared theta d theta, and that is going to be an integration by parts. Just like previously we did the integral of sine squared theta by parts, you can do the integral of cosine squared theta d theta by parts. Now, the emphasis on this video isn't integration by parts. So what we're going to do is we're going to make this integral just sort of magically appear by putting up what the actual value of the integral is so we can see how this simplifies for the rest of the problem. And so there it is. And now we can substitute this back into our problem. So multiplying this whole expression by 25 now, I get that this is 25 over 2 times theta plus 25 over 2 times sine of theta cosine theta plus the constant c. But now again, I have to remember I made up the theta. The theta is something I introduced to simplify this problem. I now need to convert back to x. Now, in the place where I simply have theta, I can come over here and solve directly for theta here. So if I divide both sides by 5 and then take inverse sine, I'll get sine inverse of x over 5 is equal to theta. So this first piece is not too bad to simplify. Sorry, x over 5. Now, the second piece, we need the value of sine of theta. Well, remember, sine of theta we can solve directly for here, right? So again, just dividing by 5, we get x over 5 is sine of theta. So that sine of theta becomes x over 5. But the cosine of theta, we have to create a reference triangle to get the value of. So using the fact that sine of theta is equal to x over 5, I can create a reference triangle. So sine of theta is x over 5, and that's opposite over hypotenuse. And so now I simply need to find the missing leg of the triangle, which will be square root of 5 squared minus x squared. And so cosine of theta, which is adjacent over hypotenuse, would be the square root of 25, square root of 25 minus x squared divided by 5. And so I can now substitute this down into the denominator as square root of 25 minus x squared over 5. That's my cosine of theta, my sine of theta, and there's my theta. And now I have successfully converted back to the original variable x. And now we could do a bit of cleaning up here. So this entire thing, 25 divided by 5 and divided by 5 again just becomes 1. So we could rewrite all of this as this times x over 2 if we want to do a bit of simplification. But otherwise, this is how we get to the correct solution. All right. So these problems, as you'll see, there's sort of really 3 steps. The first is identifying what the correct substitution to make is. The second part is correctly implementing the substitution. Once you do that, the integration hopefully is now the easy part, right? So like in this case, I mean, maybe the integral of cosine squared theta isn't easy per se, but we have a way of integrating that, whereas we didn't have a way of integrating this original function. So you take the integral, and then at the end, you simply have to convert back to the original variable. Let's look at another problem to see how other types of trigonometric substitutions might be helpful in cases where the sine function, we've seen sort of sine substitutions a couple of times now. Let's look at another one and think about what might work here. So again, notice I see a radical, a square root, and I've got this square root of x squared plus 4. Okay. My goal here in this problem is going to be to substitute something in for x so that when I square it and add 4, I will end up with a perfect square under here. All right. Now, one of the critical differences here is that I have a plus instead of a minus, right? So when I was dealing with sine, I was using something like an identity here, but that critically sort of had this minus sign here. And now I have a plus. Okay. So now I want to think about, well, what identities do I have that like might involve a plus? Well, I know that tangent squared theta plus 1 is equal to secant squared theta. Maybe that might work. Okay. Now to figure out the right substitution, I look and I say, well, I don't have plus 1, I have plus 4. So what would happen if I multiplied everything here by 4? That's just multiplying through by 4, but then I notice I could rewrite this. This is 2 tangent theta quantity squared plus 4 is equal to 2 secant squared theta, 2 secant theta quantity squared. So I think that if I substitute this in, I'll end up with, for x in this expression, I'll end up with a perfect square. I'll end up with 2 secant of theta squared after I simplify. So let's try that substitution. I'm going to substitute x is equal to 2 tangent of theta. X would be 2 tangent of theta. And of course, I have to remember that if I'm changing my x, I'm also going to change my dx. The derivative of tangent of theta is secant squared theta. So we'll have 2 secant squared theta d theta in place of our dx. So now let's make the substitution. So this becomes the integral of 1 over, all right, I have this x squared, so that's going to be 2 tangent theta squared times the square root of 2 tangent theta squared plus 4 times my dx now is going to become 2 secant squared theta d theta. 2 secant squared theta d theta. Okay, now we set about simplifying the integrand here. Now I'm going to speed up some of the algebra here a bit. If you have questions about it, feel free to email me. I want you to, or feel free to pause the video and maybe write out some additional steps for yourself. But I want to, emphasize sort of the trig pieces of this, not so much just the algebraic simplification. So that's going to become 2 tangent theta squared is going to become 4 tangent squared theta. Now remember that this under here was chosen because this ends up being 2 secant squared, 2 secant of theta squared. So when we take a square root from that, we get 2 secant theta. And then we have that times 2 secant squared theta d theta. Okay. Immediately I notice I could cancel a factor of 2. And for my own sanity, let me just go ahead and pull this 1/4 outside of the integral. I also have a secant squared and a secant, so I can cancel a factor of secant. And I end up with secant theta over tangent squared theta d theta. Now, this doesn't look very good. I'm not sort of immediately clear to me like what to do with this. And anytime that happens with trig functions, I tend to just rewrite things in terms of sines and cosines. So if I were to rewrite all this in terms of sines and cosines, secant is 1 over cosine of theta. Tangent squared would be sine squared theta over cosine squared theta. And canceling factors of cosine theta and doing top times the reciprocal of the bottom, this will become, should move this over here, 1/4 times the integral of cosine theta over sine squared theta d theta. And now, again, you may say, okay, we've done all this work to transform the integral. This isn't an easy integral, but it's now one we can do. This is a problem we can do by U substitution. So we're actually going to go over here to the side. Okay. So if I just want to know the integral of cosine theta over sine squared theta d theta, I see the function sine and its derivative cosine sitting there. So I'm going to let U be sine of theta. Then du d theta will be cosine of theta. And now substituting in, I get that this cosine of theta is du d theta. Sine squared theta, that's now u squared d theta. Those d thetas are going to cancel, and I'm going to end up with the integral of 1 over u squared du. Or written another way, that is the integral of u to the minus 2 du. And so I can just use power rule here. I'm going to increase the power by 1 and divide by the new power. And now a bit of simplification gives me that this is minus 1 over u plus c. But I made up u. U was just sine of theta. So this is minus 1 over sine theta. So you can see that at the bottom, plus c. Now I need to come back over here to my original problem and substitute in that result. So now this integral is minus 1 over sine theta. So this is 1/4 times a negative that I pick up from here, and then a sine theta in the denominator, plus c. And if we wanted to, we could rewrite this. Sine of theta is actually cosecant. And so this would be, sorry, 1 over sine theta is cosecant. So this would be minus 1/4 cosecant of theta plus c. But now, of course, we're not done yet. You sort of constantly have to remind yourself during these problems, my original problem, what was my original problem? It was this integral in terms of x. I need my answer to be in terms of x, okay? So we now need to know what cosecant of theta is, given our original substitution that x was equal to 2 tangent of theta. All right. So going back to our problem here, this is the same as saying x over 2 is equal to tangent of theta. And of course, tangent of theta is opposite over adjacent. So when creating my reference triangle, I'm going to have my opposite side be x and my adjacent side be 2. My hypotenuse then, by the Pythagorean theorem, will be square root of x squared plus 4. And now I want cosecant of theta. That's 1 over sine of theta. So that's equal to 1 over opposite over hypotenuse, or hypotenuse over opposite. So hypotenuse is square root of x squared plus 4 over opposite, which is x, and that's the value of cosecant of theta. And so now, to get my final answer, I need to substitute back in here for cosecant of theta, the new value that I have for cosecant of theta, okay? And so, and to save room here, I'm going to come over here and just physically erase cosecant of theta and replace it with square root of x squared plus 4 over x. That constant c will still be hanging out there. And so I get the final value of this integral, which is negative the square root of x squared plus 4 over 4x plus c. Again, what you're seeing is you do a trig substitution, it converts it into an easier problem, not easy, but easier, a problem that we have a method that will work for, in this case, u substitution. Now we need to compute this integral in terms of the new variable we've introduced, theta. That involved doing a u substitution. Once we do that, we get our final integral in terms of theta, and then we have to undo the original trig substitution to get an answer. I think one of the keys with these problems, there are a lot of steps here. And so the key in all of these problems is to slow down and to take it step by step. Often we get in such a rush to get to the final answer that we can become sort of paralyzed because we don't immediately see how to end up at the final answer, right? So if you sort of take it step by step, right, first I need to figure out the right substitution. Now that I've figured out what I think the right substitution is, I need to actually do the substitution and simplify the integrand. Now that I've done that, I have a new integral to consider. And now I need to figure out what method will work to integrate that function in terms of your new variable. Once you have that, now you need to convert back to your original variable of integration, right? And that could involve creating a reference triangle. I've been teaching Calc 2 for almost a decade now. I still can't look at this problem and just immediately know what the answer is. But what I do know is that if I sort of follow the steps, I can end up with the right answer. So be patient, give yourself some grace to make mistakes, but just keep working at it. And I'm always here if you have questions. All right. Let's look at one more example because this is going to involve sort of a third type of trig substitution. And if you're worried that, oh my goodness, how am I going to know which substitution to do? Don't worry, we're going to sort of summarize that after this problem. But let's take a look at this one. So sort of a similar setup, right? I've got something sitting here, and it looks like, you know, I'd really like to have a, I'd like to plug in something for x, some sort of trig function, so that this thing under the radical is going to simplify in a nice way. In particular, I want it to probably be a perfect square, right? So when I look at this, the first thing I see is that I have like something squared minus something now. Now that's different, right? Before I had 1 minus sine squared theta was cosine squared theta. And so you might sort of think, well, maybe I could use something like that. The problem is, in this case, the thing you're substituting in is to the right of the minus sign. Over here, you're substituting into the left of the minus sign. So you're going to end up with this weird sign issue. You could say, well, I'm going to negate both sides. If you negated both sides, you get this, which is true. But now the thing you're going to end up with under your radical is actually not a perfect square because of this negative sign, right? We can't really account for that negative sign. So that's not quite going to work. So we're actually going to go back to this tangent squared theta plus 1 is equal to secant squared theta. But now I'm going to subtract the 1 over, and I'm going to swap sides here. So secant squared theta minus 1 is equal to tangent squared theta. This is starting to look a little bit more like this. So I'm starting to think maybe I need to substitute in something like a secant. But the other problem I recognize here is that I don't, like, I've dealt with what happens if I have, like, the number 4 here. But now I'm fine. Like, I have a 1 here and I have a 1 there. That's good. The problem is I need a 4 here. And, well, I don't have a 4 sitting here. So the question becomes sort of, how do I introduce a 4 here without also putting a 4 there? Okay. And the answer is essentially that we want to make a substitution that will actually cancel out this 4 and make it go away. Okay. So I think the way to think about this is that if you want to introduce a 4 right here, but nowhere else, the best way to do that is multiply by that 4 and also by 1/4. Why? This 4 times 1/4, if we simplified it, would simplify to 1. But now that I've done this, I realize, okay, now I could take this 1/4 and pull it in with the secant piece. So this would be 1/2 secant theta quantity squared minus 1, and that's still equal to tangent squared theta. So I think I'm going to try this substitution here on this integral to see what it will give me. So let me just go ahead and write it here before I erase. I'm going to try setting x equal to 1/2 secant squared of theta. And let's see if that'll help us. All right. If I choose this for my x, I've got to take care of the dx as well, right? So what's the derivative of 1/2 sorry, I wrote 1/2 secant squared. That should be 1/2 of secant. That's the thing I'm substituting in. What's the derivative of 1/2 secant of theta? Well, the derivative of secant theta is secant theta tangent theta. So this becomes 1/2 secant theta tangent theta. And now I start plugging into my integral. Let's see what happens. The nice thing about this in some sense is if you choose the wrong substitution here, you'll usually figure it out because things won't simplify nicely. So it's sort of nice that there's a built-in check here. So let's see, this is going to be the integral of 1 over, now I'm going to substitute in my x. So this is going to be 4 times 1/2 secant theta squared minus 1. And then my dx is going to become 1/2 secant theta, tangent theta, d theta. Okay. So let's see what happens as we simplify some here. This thing in the denominator, right? That's exactly what I had written out before. That should simplify to tangent squared of theta, right? So you're going to square the 1/2. 1/2 times 1/2 is 1/4. And you're going to square the secant. So you're going to get 1/4 secant squared, but times 4. So you're just going to get secant squared. This whole thing will simplify to secant squared of theta minus 1, which is tangent squared of theta. So I'm going to get 1 over square root of tangent squared theta times 1/2 secant theta tangent theta d theta. Now, this integral is 1 over, that's now 1 over tangent theta, right? Square root of tangent squared theta is just tangent theta. I'm going to go ahead and pull this 1/2 factor out of the integral. And secant theta, tangent theta. And you might be starting to see, right, that this is going to lead to some cancellation here. And so after all of this substitution, I end up with the simplified integral of 1/2 secant theta d theta. Now, of course, the question then becomes, well, how on earth do I integrate that? The answer is that if you wanted to actually go through the process here, you could do some sort of a tricky integration by parts. Again, I don't want to emphasize that. So let me actually just sort of tell you the integral of secant theta d theta is the natural log of secant theta plus tangent theta plus c. Now, of course, we could check this, and it requires doing some sort of some trig work here, but you can check that this is valid. Let's just use the result here. So I get the integral of, or I get 1/2 times, oops, natural log of secant theta plus tangent theta plus c. And now all that's left is to sort of convert back to my original values here. So now to create our reference triangle, well, we need first secant of theta. That one's actually doesn't require a reference triangle. Starting from our original substitution here, multiplying both sides by 2, we see that 2x is equal to secant of theta. And so we could just go ahead and substitute that in. The secant of theta will be 2x. Plus, now we do need the value of tangent of theta. Now, there are actually 2 ways to do this. One is to create a reference triangle, and I'll actually show you that way first, simply because I think it's worth seeing. So secant is 1 over cosine. Cosine is adjacent over hypotenuse, so this should be hypotenuse over adjacent. Now, we can rewrite this as a fraction by rewriting 2x as 2x over 1, and so we'll create our reference triangle by making our hypotenuse 2x, our adjacent side 1, there's our angle theta, and so this will be the square root of quantity 2x squared, or that's 4x squared, minus 1. Okay. And so the value then of tangent theta would be the opposite over adjacent, and opposite over adjacent would be square root of 4x squared minus 1 over 1, or simply the square root of 4x squared minus 1. So you get 2x plus the square root of 4x squared minus 1 plus c. And there's our final answer. Now, I mentioned over here, there's actually another way to do this that in this case is a little bit simpler. Because you have the value of secant easily from the substitution, and you need tangent, and the fact that secant and tangent are related through one of the Pythagorean identities, instead of drawing the reference triangle, you could have, in this case, simply used the fact that secant secant squared theta is equal to secant squared theta is equal to 1 plus tangent squared theta. You know that's 2x. Marker might be running out. And so over here, this gives me 4x equals 1 plus tangent squared theta. And if I solve this for tangent squared, there should be a square there. If I solve that for tangent squared, for tangent of theta, I'll get tangent of theta is the square root of 4x squared minus 1. Right, so subtract the 1 over, take a square root to get tangent of theta. That gives you tangent of theta. You can do it either way. The reference triangle sort of works more generically, and so that's what I tend to default to, but there are other tricks available. All right, so in the past 3 examples, we've seen 3 different types of substitutions. We've seen first, actually a couple examples of a sign substitution, right? And that sign substitution helped us out when I had some number minus something like an x squared, okay? We've then seen a tangent substitution. That tangent substitution helps me out when I have some number plus something like an x squared, okay? And then finally, in this most recent example, we saw a secant substitution. That secant substitution helped me out when I had something like an x squared minus a constant, okay? And so we want to briefly sort of summarize these 3 types of substitutions we've seen and see just sort of, how we might more methodically approach these moving forward. So more generally, right, this table here sort of explains how you might deal with different types of trigonometric substitutions. So if your integral contains something like a constant a squared minus some other constant b squared times x squared, then you probably want to try a substitution of the form a over b times sine of theta. Now, we haven't been talking about this in terms of a over b's, but these a over b's are really just explaining how to pick the right constant out in front of that sign. Similarly, if we have an integral that contains something like a constant a squared plus a constant b squared times the variable x squared, then we might want to use a tangent substitution. And again, that a over b will help us choose the right constant. If we have an integral that contains something like some constant squared times x squared, some constant b squared times x squared minus another constant a squared, then we might want to try a secant substitution. Okay. These are all general sort of rules of thumb, right? And they can be really helpful. So all of a sudden, you see an integral, and I haven't worked out this integral, so don't run trying this, but you end up with something that looks like a x squared over 9x squared minus 25 dx. And you think, maybe I ought to try a trig substitution. What this table is sort of telling you is you look at this and you say, okay, I have something times x squared minus something else. Let's see, something times x squared minus something else. That looks sort of like what's over here in the 3rd row. So I ought to try a secant type substitution, but it's going to tell me how to pick the value in front of secant. So for example, here I see a 9, that's like my b squared. So my b must have been 3. And here, 25 is like my a squared, so my a must have been 5. And so for this substitution, I probably want to pick 5/3 secant theta. And sure enough, and I'm not going to work out the whole thing, but if you plug that in to just looking at sort of this part down here, if I plug in 5/3 secant squared for, or sorry, 5/3 secant theta for x, I'll get 9 times 5/3 secant of theta squared minus 25. Squaring this will give me 5 squared is 25 over 3 squared is 9 secant squared. The 9s will cancel. I'll get a 25 secant squared theta minus 25. I could factor out that 25. And I'd be left with secant squared theta minus 1, which is tangent squared theta. So I'd get 25 tangent squared theta, or 5 tangent theta squared, which under that square root is going to simplify nicely. Now, if I was going to go on to do this, I'd also have to substitute in up here. I'd have to substitute in for dx. But I'm just showing you that this is sort of the right substitution to at least ensure that this part simplifies. And that's the goal. It's just to try and simplify the integrand to have some hope of being able to use a method of integration to actually compute the value of the integral. All right, so let's try one more. So I want us now to try and find the integral of 1 over the square root of 16 minus 9x squared. So we're going to pause the video. I'm going to ask you a couple of questions about this integral, and then I want you to try and compute it. Once you've answered the questions, you can start it back up as usual, and we'll work through the solution. Okay, great. Going back to our table, I look at this and I have a constant minus something like an x squared. Looking back over here, if I have a constant minus something like an x squared, that looks like what's in this first row. So I ought to try a sign substitution, okay? Now, looking at this, I want my substitution, oops, was that a little high? I want my substitution to be 4/3 sine of theta. Okay. So again, that's looking at this 16, that's 4 squared. This 9 is 3 squared. So 4/3 sine of theta. And that's going to mean my dx is going to be 4/3 cosine theta. Okay. And now actually plugging this in, things actually end up simplifying quite nicely here. So I'm going to get the integral of 1 over the square root. Now this is where, as you sort of work on more of these, you may develop your own sort of organizational system. One thing I sometimes do is I actually go off and do some of the substitution sort of to the side. So I really want to know what 16 minus 9x squared is going to be. So I could just come off to the side here and say, okay, if I substitute in 4/3 sine of theta for x, what am I going to get? It's going to be 16 minus, if I square this, I'll get 9 times 16 over 9 sine squared theta. The 9s will cancel. I can factor a 16 out. And 1 minus sine squared theta, that's just cosine squared theta, so I'll get this. All right. So after doing the substitution, that's what's going to end up under the radical. Now I still have to take care of the dx. That's going to be 4/3 cosine theta, d theta. Got my d theta there. Okay. Now, taking the square root of this, square root of 16 is 4. Square root of cosine squared is cosine. So I get 1 over 4 cosine theta times 4/3 cosine theta. The 4's will cancel here, okay? And I will end up with d theta. And so I'll end up with 1/3 times the integral. Oh, sorry, the cosines will also cancel. And so I'll end up with 1/3 times the integral of 1 d theta, which is just 1/3 theta plus c. And now the last thing to do is convert back. I need to know what theta is. So if I come here, I don't even need a reference triangle here. I can actually solve directly. So first I'll multiply both sides by 3/4 to get this. And that will give me that theta is sine inverse of 3/4 x. Okay. And so this is 1/3 times sine inverse of 3/4 x plus c to get our final answer. All right, I just realized I sort of wrote this on top of the slide here. So let me just, to make sure you see where that substitution came from, let me actually give myself a little room down here. So I needed to solve for theta here, right? And so if I take this, multiply both sides by 3/4, and then take sine inverse of both sides, I get theta is sine inverse of 3/4 x. So that's where that last substitution came from. Okay, great. So I've given you a really extensive sort of overview here, although I say that not to say they'll be easy now, but to say we've seen a number of examples of lots of different kinds of things that could happen. And now it'll sort of be your time to go off and practice this. Again, I encourage you to sort of take things step by step. If the problem just says integrate, break that problem down into some sub-problems, right? So, ask yourself, okay, first, what's the right substitution to make? Now, can I make that substitution? Once I make that substitution, can I simplify the integrand? Once I get the integrand simplified, do I know how to integrate that new integral? Okay, and sort of, again, keep going from there, right? Now I've got my answer to the transformed integral. Now can I undo that substitution, right? Can I change back to the original variable? Okay. If you find yourself getting frustrated, email me, set up a time to come talk. We'll work through it. Okay. Now, the last thing I want you to see is that we spend a lot of time talking about trig substitutions, but in fact, they're really part of a broader class of substitutions that are also related to U substitutions. So if you'll recall from our discussion of U substitution, we had sort of written out this sort of formula that says the integral of f of u du is equal to the integral of f of u of x times, we had actually written du dx, but we could call it u prime of x dx. Okay. Now, the way we used that for U substitution, right, was we were sort of looking at something and asking, do I see a function like u of x and its derivative like u prime of x? And if so, then I could just sort of repackage all that stuff together, and I could take a bunch of stuff and collapse it down, right? So like when we did that last U substitution earlier, we took sine of theta and we collapsed that down to U. However, if we sort of think about changing variables here, so imagine I relabel all the u's as x's, and I relabel all the x's as thetas. So all I'm doing is changing the names of the variables. So this equation still holds, okay? But now this is more how we've been thinking about trig substitutions. I have an integral that's in terms of x, and what I want to do is I want to substitute in something else for x, right? In fact, I sort of want to make x bigger in the hopes of, by making it bigger, I might be able to use some trig identities or something that simplify the integral. Okay, so in this case, we see, yeah, you can do that. You plug in whatever you want for your x. Let's call it x of theta. And that's okay as long as you also change your dx to the derivative of whatever that function is you're plugging in for x, d theta, right? So these really are sort of two sides of the same coin. When we're talking about U substitution, we're often taking sort of a function that's in our integrand and collapsing it down into U. when we're talking about sort of a trig substitution, we're thinking about taking x and substituting something else in for it and coming back this way. So again, it's the same equation, just sort of using that equality in two different ways, okay? And you can also use these much more broadly. We've sort of seen an example of that at the end of the section on U substitution, but just to sort of remind you, let's look actually at one additional example. So imagine you were asked to find this integral. Now, this doesn't look anything like something that should be a trig substitution. There's no sort of x squared piece in there where I think, oh, I'm going to get some nice simplification if I do a substitution, okay? But also, I don't really know any way algebraically to rewrite that like really nicely. So, you know, I might feel sort of stuck here. But let me actually point out here that we can make a substitution, okay? So I'm going to replace x here with, I can call my variable anything. I can call it theta if I want. I'll call it w. I'm going to replace x with w minus 2. Now, if I do that, right, I have to compute dx, right? That's going to be, well, the derivative of this with respect to w is just 1, right? That's linear with slope 1. So, sorry, dx is just equal to 1 dw. Okay, and now if I plug in this transformation, this will give me the integral. Okay, x is now w minus 2. And in the denominator, x is w minus 2 plus 2 dw. And now let's see if I simplify this. This is w minus 2 over just w dw. And I can actually simplify this pretty easily, right? This is w over w, or just 1 minus 2 over w dw. And now, well, I can integrate each of these terms. So the antiderivative of 1 is just w. The antiderivative minus the antiderivative of 2 over w, well, that's the same as 2 times 1 over w. And the antiderivative of 1 over w is natural log of w. So there's my antiderivative, but that's my antiderivative in terms of w. The problem was asking me about x. So now I come back here and say, well, okay, I need to replace all of my w's with x's now. Well, if I solve this for w is x plus 2. And so I get that the antiderivative is x plus 2 minus 2 times the natural log of x plus 2 plus c. So again, here, what did I do? I chose a clever substitution here that allowed me to rewrite my integrand in a way that made it really easy to integrate. There are many, many types of integral substitutions, many, many more than we could ever possibly talk about in this course. So in this course, primarily, we've talked about U substitutions. In this video, we've talked about trigonometric substitutions. But I just want you to know that there's this whole other world of integral substitutions that can be really, really helpful. In particular, if you go off into certain areas of applied math where you're working with integrals of certain types quite often, you may in fact learn many of these substitutions. But we're not going to focus too much on learning lots of different types of substitutions, just the two we've already seen. But I want you to know that this is sort of a bigger piece of the mathematical world that you could learn about.